Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on August 4th, 2025. So just yesterday. This paper introduces a framework that significantly improves a model's ability to follow instructions without hurting its reasoning skills, and it does this without needing a stronger, external model for supervision. The paper is titled, Beyond the Trade-off, Self-Supervised Reinforcement Learning for Reasoning Models Instruction Following. And as we'll see, the approach is both scalable and cost-effective. It tackles the classic problem where making a model better at reasoning often makes it worse at following instructions. Also, the authors shared their official implementation on GitHub. If you check it out, you'll find all the code and scripts plus some really detailed instructions. They walk you through setting up the environment and the entire training pipeline, from the reward model all the way to the final RL step. Alright, and this first figure really visualizes the core problem and the proposed solution. This radar chart plots performance on reasoning tasks over on the left and instruction following tasks on the right. Now, the key thing to notice is how the improved models, shown by the solid lines, get much better at following instructions. You can see their scores expand way out on the right side, while the reasoning scores on the left remain just as strong, or even a little better. It neatly breaks that trade-off we were just talking about. So this diagram lays out their two-part framework, starting with the reward model training at the top. Here they use what they call an Incremental Constraint Curriculum. This means they teach the model by starting with a simple instruction, and then gradually adding more and more constraints, which gives the model clearer, step-by-step feedback. Then, in a second stage, the reinforcement learning training, the system learns to follow both hard and soft constraints. Hard constraints, like formatting, are checked with simple code, while soft constraints, like tone, are judged by their new reward model. This table then details the statistics for that incremental constraint curriculum we just talked about. You can see the 5 levels, from L1 to L5. As the model moves through the levels, the total number of constraints it has to follow grows dramatically. It starts at just over 2,800 constraints in the first level, and by the final level, L5, it's dealing with over 13,000. This gradual increase in complexity is what helps the model learn to handle complex instructions without getting overwhelmed, providing denser training signals. Okay. Moving to the results, this table shows the overall performance on a whole suite of benchmarks. These are split into in-domain tasks, which are similar to the training data, and out-of-domain tasks, which use completely new constraints. The key takeaway is clear when you compare a base model like QN 2.57b Instruct with its improved version right below it. The scores are consistently higher across the board. This pattern holds true even on the challenging out-of-domain tests, which shows the framework generalizes really well. Alright, so to really test what makes their method work, the authors ran an ablation study. That's where you systematically remove key components to see how performance changes. This table shows the results. The top row is the full model, which gets the best scores across the benchmarks. But look at the rows below. When they remove the rule-based reward, the probability reward, or that incremental constraint curriculum we talked about, the scores drop. This really proves that all those components are necessary for the model to work so well. Alright. So after seeing what makes the framework tick, the next big question is, does this specialized training hurt the model's general skills? Well, this table looks at exactly that, showing performance on several general capability benchmarks. If you compare the base QN 2.57b Instruct model with their improved IF version, you can see the average score actually goes up. This is a crucial finding, showing their method enhances instruction following without harming the model's core reasoning abilities, and in some cases, even slightly improving them. So to wrap things up, the key takeaway here is that it's possible to break that stubborn trade-off between reasoning and instruction following. This self-supervised framework manages to significantly boost a model's ability to follow complex instructions, all without needing external models, and while keeping its core reasoning skills intact. That's it for this episode.